sensors and software team for their time and giving us instructional webinar on the Pavement Density Profiler system. I just want to clarify that the purpose of this webinar is to train FHWA NDE labs, engineers, and technicians. So Ferrohighway does not endorse any products or manufacturers. So this webinar is not intended to reflect a preference, approval, or endorsement of any system. That's all I wanted to share with you in the beginning of the webinar, and I'm looking forward to the webinar. Thank you.
Great, thanks, Hoda. We're here to try and provide some insight into this whole business of using GPR, ground penetrating radar, for pavement density assessment. So we tried to assemble a presentation that's as much educational as anything else and shows what we're doing and how we do it with our devices, and just to try and share some of the ideas, fundamentals, and so on. So that's what this presentation's about. We're trying to balance between getting too technical and just giving an overview. So if there are topics that people want more information on, make sure you let us know, because we have a fair degree of insight on these things. And if there's things we don't talk about, ask questions about those too. So we will go through this. It should take about a half an hour, 35 minutes to go through the formal presentation. So on that note, we'll get started. Just so you know, I'm Peter Annan, and I'm presenting this talk today. I have a long history in GPR, and my primary focus has always been devising instruments and making methodologies to map soils and rocks and anything else that we can find in our environment, including engineered materials such as concrete and asphalt pavements and so on. So that's who I am, just for reference. You can find out more about me if you go to our website or Google me, but I won't belabor that. So we'll go through some of the topics I want to get through today. So we'll go through who is Sensors and Software, just give you a quick history of us, not too much detail, why pavement density, and then what is the Pavement Density Profiler, so you get a sense of that. One of the things that I've found is that people don't have a good understanding sometimes of indirect measurement principles, so I put some topics on that just to help out and clarify what we're doing and why there are some challenges and differences in how these various methods can be used. Some commentary on future routes, and then just summarizing and hopefully opening up for questions. So who is Sensors and Software? We're a company that is specialized in designing and building ground penetrating radar systems, and we have a whole family of products which we build and ship around the world to various technical, scientific, engineering, and related type users. We build about 1,000 systems a year, so we have a good handle on what it takes to make these things work properly. One of the things that we do have is a highly skilled team of scientists and engineers who really dig into the fundamentals of making the kind of measurements we're talking about today. We're always developing new methods and devices, and we have a long history of measuring material properties and understanding the properties of various kinds of materials and what is important and what isn't. So that's Sensors and Software in a nutshell. Now, why pavement density? This is a topic which is fairly interesting to a number of people who are in the road construction business, and so I thought we'd get through some of the basic background, the standard approach, and then some of the non-destructive approaches. So what's the background here? Well, for at least 20 years, people have realized that the density of asphalt, or the consistency of placement of asphalt pavement, is a big factor in determining the roadway lifetime or life expectancy. And this has been pushed out by a number of groups, but the head of Federal Highways Administration has been a leader in this, and so is AASHTO, and there's a number of documents and reports and so on which really demonstrate this is important. So the consistency of asphalt pavement comes down to quite often looking at the density of the material and how well it was placed. So how uniform is it? And so there's a whole raft of material you can go back and look at, so I won't belabor that. But that's what drives a lot of what's going on today in pavement density measurement. So what's the normal way that this has been done? Well, normally the go-to approach is using a core. Essentially, you take a core and measure its density and come up with a assessment. If you have enough cores, you can look at the variability along the roadway. One of the big challenges here, however, is where to sample, and the method is destructive. How many samples should you take? You got a turnaround time to make the measurement of density in the lab. So there's all sorts of challenges. They're practical, and you have to live with them. And this just summarizes the basic issues. Coring, you can see, leaves a hole in your nice newly paved road if you're looking at that. You have to go through and get some estimate of the core itself, look at its properties. You have to measure its density, and normally that's simply done by measuring it wet, then measuring it in air, and then measuring it in water. And that gives you both a mass and a volume, which you can then convert to density. And so that's basically the traditional way, and it's the reference point for everything else that's done. Now, what are alternate approaches to this? And this is where you get into the non-destructive evaluation methods like GPR and the Pavement Density Profiler and so on. And alternate approaches are essentially you want to achieve on-site results. In other words, they're immediately available. You want to have non-destructive approaches if you can, and it should be simple and fast so the measurement isn't too complicated to do and a number of measurements can be made. The alternate methods that are out there and used now are the nuclear density gauge, which is based on a density surrogate, which is the gamma ray scatter from the material. The PQI, or pavement quality indicator, measures the dielectric permittivity of the asphalt pavement, and it does it by a capacitive type measurement. And then you have GPR, which measures the dielectric permittivity, and there are a couple of ways that's done. So these are alternate methods for measuring density, but the key thing you will note is they're all indirect measurements, in the sense they measure something else and then use that measurement to infer the density. They don't measure the density directly, and we'll talk about that a little bit when we get to the indirect methods. So what is the Pavement Density Profiler? It uses GPR, and so we'll just go through some of the concepts. This is a device which we've developed at Sensors and Software over the last 3 or 4 years. We've made these kinds of measurements for, probably 15 or 20 years, but we've only turned it into a commercial product now. So what is the concept here? What we do is we have a device which sends out a radio wave, and it's transmitted from a transmitter here. The signal impinges on the road surface and it bounces back to the receiver here, which detects the reflected signal. In terms of what the data, raw data look like, you measure a signal amplitude, and the first signal is signal that travels directly from the transmitter to receiver, so that gives us a reference time. Then we look for the reflection from the surface, which is the next event that comes in. And so it's a signal that travels this path down and back up. And that's the signal we want to look at. And we look at the amplitude of that signal. And that amplitude turns out to be an indicator of the dielectric permittivity of the material, in this case, the asphalt pavement. So first of all, we have a device that measures that amplitude and it converts it into permittivity. So that's the first step. And that's really what the pavement density profiler does. It enables this kind of measurement, excites the radio wave that travels down, bounces back, then records the signal amplitude of the reflected signal, and then with appropriate mathematical manipulations, it turns it into permittivity. So that's the first step. The second step is to turn it into density, which is known as the permittivity to density or K to rho conversion exercise. And this is the usual challenge. We normally would look at permittivity, but converting it to density is part of the second stage of using any of these devices, as we'll see in a minute. So what does this thing measure? Well, it puts the signal down and it bounces off the surface and it detects a certain volume of the asphalt pavement. And so the volume is dictated by two parts: the area which energy impinges upon here, the top of essentially a cylinder, and the depth the signal penetrates into the material. And these are part of the instrument design factor. In the current PDP, we designed it so that we had what's called the footprint here equal to one Fresnel zone, which is a zone of influence, which is technical jargon, but it really has the essence of saying that most of the energy comes coherently from an area which we can define. And so that area is defined by the antenna directivity, height of the antenna, and the bandwidth of the system. That's the frequency range the system measures over. The depth of exploration here is a function of bandwidth and the way we process the data. And so what you see in this little illustration here is the effect of a layer at depth. And typically, depending on how you process the data, you'll get the right answer here. If the layer gets too shallow, it starts to distort the data that you would measure. And so the point at which this curve goes flat is the depth of exploration, essentially. It's a complicated detail here, but it's a concept which is important to understand, and that's what defines what your depth of exploration is. So as part of your system design, you look at these parameters and try and get them so they're optimized for a typical requirement. So what does a PDP look like? Well, it's just a black box like you see here sitting on this cart. And this contains the transmitter, the receiver, all of the electronics to make the signals, the computers to process the data, and it's all self-contained and battery operated. It sits on a cart. In this case, the cart is used as the platform to roll it along so you can do profiling with the device because it can measure continuously. The positioning is controlled by an odometer, which is on one of the wheels. You also have the option for having GPS. The unit itself has an internal GPS for positioning. And the data shows up here on a tablet, which is linked by a wireless path to this device. So the unit itself runs independently of the tablet. The tablet essentially is a display device, starts and stops, but other than that, everything else happens in this box. So you can have one box or several boxes running, and you can look at a multiplicity of data sets. The data is all self-contained in here, which you can export on demand to a CSV file, which allows post-data acquisition analysis. So that's the PDP in a nutshell. One of the key things about it is it's calibrated at the factory. It has a long-term stability, which we've been evaluating for 2 or 3 years now. It's easy to use. You go to site, you essentially set up, put it on the cart, push the button, power it up, and in less than 5 minutes on a site, you can be up and running and collecting data. The way it's set up is it has 2 modes of operation. One is where you can just go to a point and statically measure, or you can also turn it into a profiling mode where you just push it along and it collects data at regular intervals. So that's the PDP as an instrument. In terms of what is the volume it senses, the surface area here that you like it is about 30 centimeters or 300 millimeters in diameter. And the depth of exploration on the default configuration is about 100 millimeters or about 4 inches. Normal operation, you sample every 100 millimeters, and that means you get roughly 3 samples per area of the footprint here that you're looking at. And that again is designed to be optimal for the deployment of the device. Most of these elements are adjustable to some degree based on exactly how the instrument is set up. So it can be customized to do other things. But we selected these parameters based on what we saw as the typical variability of asphalt pavement and what made sense for site evaluation. So what does it look like when it's in operation? Well, essentially, if you're in profile mode, you can be pushing the unit along and it will collect data continually, and you'll see it on the screen like this. In this case, where you can see a profile of the permittivity going up and down as the cart moves along. It also gives you the number and the position of the device and so on. So this is all there, and you can see it in real time as you go. The other modes of operation are the same. If you go to a static mode, you can see that. If you want to look at a histogram of the data set you've got, you can see that. And all of the data can be exported, as I said, in CSV files. So much of this can be analyzed afterwards in a variety of tools. In terms of deployment, we primarily focus on the cart deployment because it's simple, easy, and readily used. Mounting on a vehicle usually requires some sort of customization of the vehicle itself. In this case, we have it mounted on the back of a vehicle on a trailer hitch. Many people prefer to have the device on the front of the vehicle up here, and that's more of a customized mounting exercise. So unless you have a specific vehicle you're going to commit to, then first order uses are typically in this form with the cart. The other question comes is whether or not you want a vehicle on the road behind your paving train when you're out there when the asphalt's still hot. You may want to have the lighter, simpler device like this being used. We show a single unit here, but in principle, these are all independent units, so you can have as many as you like mounted on the vehicle and measure multiplicity of paths as you drive along. Similarly, you could have several carts running along here. So deployment is really a matter of what the application demands and how the user really wants to use it. These are just a couple of examples where it's sites we've been out and worked on. And one of the things we do a lot of testing is to compare the PDP to things like a nuclear gauge here or a PQI device, as well as cores. So a lot of our activities are really assessing the methodology and optimizing the system. So we're always doing those kinds of experimental tests and trying to evaluate what are the tricks of the trade, so to speak. An example of data This is some data where we collected in both stationary point mode and in profile mode. And you can see the response measurement here. This is about a 60-meter line. And the profile here has been repeated twice. You can see there's almost a perfect overlay between the two passes. And that's the continuous profile. And you can see the black dots are the stationary points where measurements were made. So you can see they're self-consistent, and it's really a matter of what manner of approach you would like. If you're trying to calibrate permittivity to density, then you quite often will use the stationary mode. You'd look at your profile data and say you want to look at a low spot and a high spot, and so you go back and do repeat stationary measurements there to get a good reliable permittivity value. Then you would do coring at this point, and then you'd build up your correlation curve between density and permittivity. So that's why the two methods are there. One of the things that we do, and we really encourage people to do, is have a site which is relatively controlled, that isn't going to go away or get destroyed or get changed, and then test the instrument on that regularly. It's part of a QC validation of the instrument, and we spend a lot of time as designers and builders doing these kinds of tests because they tell us how good the equipment is and how reliable it is. And this is just an example of 5 repeats over the same line, and you can see the data pretty much overlies each other. The variability we normally see is we just don't get back to the same physical position perfectly every time. One of the things that is used a lot is a histogram of the data just to look at the consistency or the variability, or what does the sample population look like. Again, this is part of one of the displays that comes out in real time, and you can also look at the data afterwards like this if you analyze it through a variety of software tools. One of the things we found extremely interesting is to look at the variability between instruments and the same instrument over time. And we have a test line near our office which we use regularly, and this top curve is the result of multiple systems operated over this line for a period of about 3 months. This several hundred repetitions of passes over this line, and you can see the consistency between units and with time. And again, at the bottom, you can see sort of the average and the deviation from that average. And what we found again is that a lot of the variability is just the imperfection of getting back to exactly the same spot over and over again. And in this data set, it's interesting because we have an old asphalt here and an old asphalt here and a new zone of asphalt in here. And you can see the joint right here is one of the joints right there. And this new asphalt is quite a bit more uniform than the older asphalt shows, but you can see the differences and you can see the consistency. One of the other things you do is you measure multiple passes over an area to build up a map. So essentially this is many profiles to give you area coverage. You can do simple profiling, like you travel back and forth along one direction along the area, or you can do direct measurements in both directions this way and back and forth across and build up your map. The right shows you an example of this, which is from the Caltrans test site. And you can see a number of features in here. You can see some low density areas, some high density areas. You can see the joints between lifts and so on. So there's a lot of detailed information in this figure. And it's the kind of thing that people do when they're looking at a section of road in detail. Again, this is just a matter of how you deploy the instrument and how you want to collect the data. If you just want to have a simple solution, you may just want to have a profile down a lane or a lift, or you may want to have a multiplicity of paths down here to look at the area. So lots of different variations on how you can collect data. Another example here, one of the things that became obvious to us early was that we could see a lot of variability at the joint between lanes, and this shows up very clearly in this example from Sweden, but we have a number of examples like this, and so it's an interesting way of using GPR data. And one of the things we found is it's usually better to do the profiles across the road like this, and then you can see the variability in the joint. When you run parallel, it's harder to stay aligned with the joint, so you get a much fuzzier picture of what's going on at that joint area. Again, optimizing your methodology for a particular application. So that gives you an idea of what the pavement density profiler is designed to do in some of the results. The next thing that I thought I'd get into is the fundamentals of indirect measurement. This is a topic which doesn't get adequately addressed, I don't think, so I thought I'd just put a few points from one of my other talks in here to stress the ideas. What do we mean by indirect measurements? Essentially, we find something that's a surrogate for the actual thing we want to measure and measure that instead and use it to infer what we really want to measure. We do that every day, and you will see it everywhere you go. Air pressure altimeters in aircraft in the early days, they measured altitude by measuring the air pressure. And then they had a gauge which would show what the altitude was, but it was really just a measure of air pressure. Things like bimetallic strips are everywhere, and essentially these are two strips of metal which have different coefficients of expansion. And by putting this together, you can make something which bends or twists as the temperature changes, and then you can attach a gauge to that, and suddenly you have a temperature gauge. Echo sounder on a boat, you look at the time of flight of sound through the water to the bottom and back up again and display it, so you're measuring travel time to indicate water depth. So these are all examples of indirect measurement, and one of the things I think we all depend on these kinds of devices, and there's always pitfalls, but people adapt and get used to the shortcomings by either revising the device or just overlooking some of the problems because they're useful in their own right. So that's what an indirect measurement is. When we're talking about density, what are we talking about? We're talking about the amount of matter that's in a given volume. And the matter is really the protons, neutrons, and electrons, which are forming the atoms of the materials in any particular material we look at. So what is a density surrogate? If we can measure the number of these particles in the volume, we have a surrogate for measuring density. And just as a simple by note, the number of protons is pretty much equal to the number of neutrons, and it's equal to the number of electrons. So if we can get a measure of any one of these, then we have a measure of the amount of mass that's in a given volume. So that's basically how indirect density measurements are made. And there's two approaches. One is to use gamma rays, and you impinge these on the material and you look at how many bounce back. And that's a measure of how much nuclear materials in the material you're looking at. Another approach is to use electric fields or electromagnetic fields, and they detect the charge matter in there, which are the electrons and protons. And so both these methods are looking at those fundamental building blocks of material and trying to get a sense of how many are in a unit volume. The nuclear approach is well known. It's been around for many, many years, and it scatters energy primarily from the neutrons and protons because they're the more massive items in the material. You count over a period of time, and that gives you an idea of how many are there, and then that's used to estimate the mass. If you have a way of getting the volume, then you can get a density, or you may calibrate against known materials with known densities, and then calibrate the count against the density. The electromagnetic approach, you apply an electric field and see how polarizable the material is. Essentially, the electrons and protons in the material will move when the field is applied, and this polarizes the material and can be sensed. So this can be sensed either by making a capacitive measurement of the material, or looking at how the radio waves travel through a material, or how they bounce off a material. These all depend on the polarizability or the permittivity of the material. Again, if you can have a volume estimate, then you can get a density. Otherwise, you calibrate to get density from known materials and the K from the measurement, and calibrate your conversion curve that way. So, conversion to density, you can transform the indirect measurement to a mass, estimate the volume, and then work out a density. More often you calibrate, make a measurement on a sample like a core, measure the sample with the indirect method, then develop a conversion relationship. And that's part and parcel of what we do with all of our indirect measurements. What are the challenges here? Well, the big challenge is the volume sampled is difficult to quantify. I showed you earlier how the GPR reflection method does it. We look at the surface antenna pattern and the Fresnel zone, and then we look at the depth of sensing to come up with a volume. But it's not a uniform sensing, and that's true of all indirect methods. Generally, if the sample you're looking at is not uniform, the instrument averages in a way that isn't necessarily a uniform average, but it's a weighted average. So those are part of the challenges in making these measures. Sometimes the instrument itself may introduce errors or be unstable, and then you have even more problems. You don't know whether the variation is from the instrument or from the material. So all in all, developing the conversion relationship is challenging. And even though it is, it doesn't mean that it shouldn't be used. And one of the things that does come out of this is you find indirect measures are highly useful even if the two instruments don't give the same absolute numbers. That's because they're looking at slightly different volumes or different weighting in the volume. But at the end of the day, the variability over an area is certainly indicated by the indirect measurement. I just thought I'd throw in a snapshot of all the methods. I don't know how many people have used all these methods or look at them, but I just thought I'd just review them quickly, just because it's those things that people don't always see. Core density, we've already talked about. Essentially, you have a coring unit here, you drill a hole in the asphalt, take out the core, then measure its weight and volume to get a density. Very widely used, standard, I would say it's called the gold standard. The nuclear density approach, you'll see a variety of devices like this which contain a radioactive source which generates gamma rays which travel down into the pavement, and then there's a detector which records how many come back. Quite often you don't just measure at one spot, but you'll have a pattern of measurement. So here you can see a number of placements of the device to get an estimate of the density over an area. One of the things you find with nuclear gauges is that quite often a multiplicity of measurements is very helpful, because slight variations in surface roughness can change the data values. The PQI is a measures the dielectric properties of the material. The silver device down here is essentially a capacitor which couples into the asphalt underneath it, and you measure the capacitance of that device, which in turn depends on the polarizability of the material, and that's an indication of the dielectric constant. And again, you quite often will measure not just one point, but several points to cover an area to get a good, reliable representative value. The radio wave velocity approach is one most of you probably won't have seen, but it's one that we've used a lot over the years. And essentially what you're doing is you're varying the separation between your radar transmitter and receiver. The rays signals will travel a multiplicity of paths between the transmitter and receiver, and you can measure the speed of propagation of these signals, and that in turn gives you an estimate of the permittivity. In this case, is one transmitter and several receivers, and the whole unit is profiling along to get a continuous profile of velocity. It's a rather complex system to use, but it's great for research purposes. The surface reflection approach with GPR is extremely simple, and it's one of the ones that we've just talked about. And the reason it's popular is it is simple, it's reliable, and it gives you a profiling capability as well as a point measurement. All the other measurements are point measurements or very localized measurements. The advantage of the profiling approach is you can get a continuous look at what's going on. Then when you want to convert to density, you measure samples. In this case, we're looking at compaction, which is the normalized density on the left here, and the permittivity from the PDP device along the lower axis. And so you get a conversion curve which translates the density or the permittivity into the density. And this is a very common way of doing the permittivity to density conversion. The challenge here is that it requires a number of cores or a number of other samples to be able to create the conversion curve. And in our experience, generally, the success of this is extremely variable. People who are very diligent, who take very carefully positioned core samples, and a large number of them can develop this curve very well for a particular asphalt. But it isn't always successful if there's only a few sample points. And this is the challenge. So it's always a trick to be able to get really reliable permittivity to density conversion. The various methods allow you to get data from different sites, and the method comparison, there's a number of reports out there, and this is an area which is still one which we find intriguing because all of the methods that are available all give different results from one another to some degree. There's seldom a perfect correlation between the various methods, and this is always challenging when you're trying to evaluate the performance of a device. So these tests need to go on, and there need to be more of them when we start comparing all of the devices. So a lot of work in this area is still going on, and everybody is getting quite a bit wiser about how to use these tools and what their idiosyncrasies are and how they compare. And part of this is just the volume they sample. They look at slightly different volumes, same thing with positioning. If your core doesn't come from exactly the same position as your profiling data, for example, then you will have an uncertainty in your results, which is hard to explain. And so positioning becomes extremely important. One of the other things which I threw in at the end here, because it's a topic that comes up all the time when we're dealing with GPR or dielectric measurements, is that the presence of water impacts the permittivity and can result in strange readings or abnormal readings. And this is again that test line I showed at the start with the PDP. And we made measurements for many, many days, and generally we would go out when it wasn't wet. So if it had rained, we would skip and wait till the next day, that sort of thing. And so we got very consistent results, which are what you see on the top here. Then we wanted to look at what happened with water. So there was a day when it rained, and so we went out. While it was raining, you can suddenly see this brownish line here is the impact of water. This area in here is the newer asphalt, and the water seemed to collect in that area, and you can see that there's an abnormally high permittivity, which is due to the presence of water even in a thin film sitting on the surface. What was interesting though is that after a day or so, the area dried out and we went right back to normal. So what this says is liquid water present on the surface may affect the data, but once it's dried out, then it goes back to normal. And this has been observed in a couple of different places now. So it's a useful thing to know. So if there is water on the surface, you need to be cautious about using a dielectric measurement, because that water can strongly affect the observed permittivity. So one of the things that we see a lot of is how do we practically use the PDP or any of these devices, but the PDP especially because it collects a lot of data. Should we use it as a core-like measurement where we make point measurements? Is it better to have profiles and then core the anomalies? Should we use full area maps and core the anomalies? Should we use the permittivity as the variable to map instead of density, so we're not struggling to try and get a density to row conversion? How much effort should we spend on permittivity to density conversions for practical use? What's needed to get best construction practice? Many of the people we talk to want to use their measurements to adjust the construction practice on the go, and that means getting fast turnaround of data. And what's critical is the uniformity and not the absolute numbers per se. On the other hand, you have certain jurisdictions dictating that the density has to meet a certain number, and there's pay incentives or penalties which are placed on using that absolute density number. So there's all sorts of interesting challenges out there for the community to deal with. From our perspective, the use is still evolving, and we see many paths depending on who we work with and who we talk to. So lots of interesting things for people to assess as we go ahead. So, summary from our perspective, we've been designing an instrument that's fit for purpose, designed to hit the application. It's factory calibrated, so you don't have to spend a lot of time adjusting and fiddling in the field. It gives you point, line, or area coverage. You get high spatial density sampling, so you can cover a lot of ground and get a lot of samples. You get immediate results, and it's simple to use. So that covers what we wanted to get out today, and hopefully it's been helpful to you. If you've got questions, we'll try and answer them. And
so the first question that was asked was, what is included in the factory calibration?
Okay, so the factory calibration, essentially what we do is we measure the instrument response. Everyone is calibrated in the factory, so we know exactly the voltage level of the signal that comes out. And we make sure that's stable with voltage, temperature, and everything else, so that that unit will make the same measurement over and over again. That's part of what that repeatability plot shows, is that we're taking that voltage number and we know what it is when the device is placed over certain targets. So we're all calibrated, and that number is what's used to convert or generate the permittivity. So some of you have may seen devices where you go out in the field and you put out a metal sheet and you run the device, then you get a number, then you have to enter it in and so on to calibrate with. That's all done at the factory. The instrument is calibrated that way and gives reliable, stable results. And we've had these things running for 2 or 3 years now, getting consistent results. So we're that's part of the effort that goes into the instrumentation. It's not a trivial exercise to make that happen. So when we say it's factory calibrated, it comes out and you can take it and it gives you a permittivity.
Okay, and then there's a bit of a related question there to ask if there's a need to calibrate the device before each project to get density values.
That's a different, that's why I was pointing, and I think maybe I should go back here. Yeah, that slide's here. This slide has these 2 points down at the bottom, okay? So what the instrument does is it measures the permittivity. So this amplitude is what we use to measure permittivity, and that's what we calibrate at the factory. So the voltages, the signals are all stable and well known, so we know exactly what the permittivity will be within a certain tolerance or instrument sensitivity, which is very, very tight. So this function to go from the amplitude to permittivity is in the instrument, and that's our, what we call instrument calibration or stability. Or the second step is to convert the permittivity to density. And this is the step that's always a challenge because it's non-unique in the sense every pavement is really different, so that this conversion relationship is different. So that's where we would then jump to something like this, where we do a permittivity to density. What you have is actually samples which are measured at specific spots, and then you fit a curve to them or a line. A number of variations on a theme here, but the idea is you come up with this relationship, which is density related to the permittivity, and this is your function G in the last slide, and that's the one that has to be done on site. And that's why some of the people are now talking about using the permittivity instead of doing this conversion, because this conversion has turned out to be difficult to do in a reliable fashion. So I'm not sure if that answers all the questions. So the calibration in the field is this estimating the permittivity to density, and there's a number of ways this is being looked at now. Some lab measurements to do this and so on. So but it's the weak link if you want absolute densities. But if you are looking at relative variations, then you get a really good handle on that from looking at the permittivity. And there are empirical relationships that convert permittivity to density, but they may not be exactly right for a particular site. There's another step in here that's part of calibration. We don't call it calibration, we call it validation. And I think this is also an important point. And when you're doing this kind of work, you need to validate that your instrument's working properly. And so we have a number of ways we do that. One is we have a standard test line, which we would use, for example. We also have a standard target, which we would measure, called a validation target, and so on. And what these are, they're for the technician who has to run the equipment. It gives them a way of, I go and I follow step A, B, and C, and it gives me an indication that the instrument is working properly. And so it's a validation step, which I didn't spend much time talking about, but it's an important part of any of these devices. You have to be able to validate they're working properly. There's no sense of going out and making all sorts of measurements only to discover the device you used didn't work right.
Is it possible to calibrate the PDP based on stationary measurements?
Yeah, that's an interesting question, because we have been looking at that ourselves. This was one of the examples, is point and stationary we've been looking at. In principle, if you set up the device over a point, you can average for a long time and get a very accurate permittivity measurement. And in principle, because you're not moving, you should be able to core right at that same point and then get a good correlation between the core and the static measurement. So that would be the logic of making a point measurement with the density profiler, and then measuring and comparing it with the core. So you're doing that approach. The other one would be just to use the moving measurement profile here. And that was part of the reason we do these static measurements, was to make sure that the mobile platform as it's rolling along gives the same result as a static measurement. And from our experience, within the error of positioning, which may be a few centimeters, is the point and the rolling measurement are the same. So that then begs the question, how do you get a conversion curve? And what you want is enough variation in the permittivity to give a good variation in the density. So in other words, if you came along and had a flat profile here with no variation, you'd really only have 1 point. And presumably that's 1 point on that calibration curve. So ideally you want a long enough stretch of line that you can see extremes in the data. So you can see lows and highs, and ideally a number of them, so you can get enough representative values of different permittivities and presumably different densities, so you can actually build that calibration curve. And so it certainly is tens of meters of line are desirable to get enough variation. And we have seen some lines where it's almost perfectly flat, so there isn't significant variation. I think the next slide, in fact, I had in here was a lot more uniform. You can see this with quite a uniform line. There's still variations, peaks and troughs here, but some sites you'll see the permittivity will go from 6 down to 4, and you'll have quite a large range of variation. And sometimes you'll have a very uniform asphalt with very little variation. So you want to do enough that you get a significant range up and down to ultimately build that calibration curve, which is like here. So you want to have a range of permittivity, and hopefully you're spanning the full range of compaction in this case. So I'm not sure I answered that as the absolute number, but that's what you're trying to do here. If you have a very uniform set of data, all the data will lie, say right here, you won't have enough range of samples to be able to build a conversion equation.
There's a question about the size, I guess, of the footprint, or based on the surface area, 300 millimeters. I assume it can be used for lab specimens of 12 inches.
Yeah, that could be done. And there is a rationale for that, in the sense that we talk to a lot of people and trying to get a sense of what is a significant volume, and that we should sample. Okay, you could make that footprint smaller by lowering the sensor and raising the frequency, but the real key that we found talking to people is that sort of areas on the order of, half a meter or more are significant. Things which are 5 or 10 centimeters across are really not that significant in the scheme of things. So, and that's why you see people quite often doing multiple cores, is that to get a representative sample, you may need 4 or 5 cores in area to get out to that larger area. And so as we were designing the device, we designed it to be roughly covering up to about a half a meter. The majority of the signal is in the range I said there, which is about 30 centimeters, but it does have some overlap out of that. The volume isn't perfectly cylindrical. And that's one of the points I made there as well, about exactly what is the shape of the volume, and all of the devices that are indirect have a slightly different volume they sample, and they weigh data from, or information from, different depths differently. So it makes them hard to make absolute comparisons.
Okay, I think there's one more related to this, and then we'll move on to some of the other topics. Just I'm trying to group them together. If you took two cores on a long profile, one at the highest K and one at the lowest, would you feel confident using that for the K to density conversion?
I think that's fairly practical. Where I would get concerned is if you want to look at the compaction number and start using that number to penalize or incent a contractor. If you want to look at it as a way of getting to a quick density from the permittivity, I think it's fine, and that's the way I would do it in practical sense. It's quick, simple, you don't need too many cores. I think I'd probably do more than a couple of cores, but that idea, do the high and the low, and that should give you 2 points on that line, which you can then use for your conversion. It should be reasonably okay. We're building up experience with doing that. We first went down the rabbit hole of trying to do a lot of correlation between cores and permittivity measured with the PDP, and we found it was really hard to get that data. Invariably on a stretch of line or road, you'd have a dozen cores at most, and it really was hard to have confidence in that. So, and there was a lot of variability because we thought that people weren't necessarily getting the cores at the right locations, so it was a disconnect between one set of measurements and the other. So we've had challenges. So getting coring done close to when you do the measurements at high and low spots was probably going to be as reliable as any other approach to it.
Moving on to another question. So questions about multiple lines, I think. There was one question saying the Caltrans density heat map was generated by many survey passes. If right, how many would you need to generate the map? And how to interpolate density between any two passes. And then a second related one is if you were doing, say, a vehicle mount with 3 PDP units, can your software map multiple lines of data on the same map? So I think those two are somewhat related.
The critical thing is if you start looking at the footprint of the instrument, you want to have your lines so that the footprints overlap. If you suddenly start running lines so that each line is further apart, so these areas of illumination don't overlap, then you have gaps in the data. And so you really want to make sure if you're doing an adequate data sampling and you really want to build a proper map, you have to adequately sample the data. And that means having the footprints overlapping between adjacent runs. So in this case, you'd want to be doing stuff at probably a ½ meter or less spacing, okay? If you go beyond that, then you're depending on the interpolation between the measurements, and that's as good as the variability you're dealing with. If you have a lot of variation, then you may not have a very good map. If you have a very uniform environment, then you can probably get away with it. So it's I wouldn't say it's unique to the pavement density profiling needs, but it's typical of any set of measurements. So I'm sure you could go out and take a dozen cores in the same area and contour that, but how reliable would that be? So my confidence would be start to go down if I had much more than, if my footprints here didn't touch each other, I'd start to get concerned about the reliability of the map. Then you get in, if you have sparse data, then you get into the usual contouring, kriging, statistical approach to how do you build your contour map. So if I were doing a lane right now, I don't think that 3 units mounted on a vehicle would adequately sample a whole lane. With the footprints we have right now, I think you want to have 6 or 7 units across the lane to get adequate full lane coverage. I think there was a second question to that about making maps and
Making maps out of multiple lines
yeah.
of data.
We don't normally do that in real time. In some of our devices, we do it. The trick is to be able to have all of the data together at the same time to build the map image. And we call that grid mapping in a lot of our products. And so you'll actually put a number of lines, you'll traverse them and build the map in real time. With the PDP, it's been a question mark as to whether that was a primary use. So what we do is we just collect each line as an independent and then export it and use one of our mapping tools to build the map. If there's a demand to make a real-time map where you go out and do 10 lines and then convert them to a map right in the device, that can be done fairly easily because we do it now. But it hasn't been an application that we approach it that way. So we treat each line as an independent line, then we put it into a software package that essentially does the gridding for us or the interpolation and build up the gridded data set which the color map or contour map is generated from.
Surface materials, if you have dirt or pebbles
right,
or
yeah.
other things on the surface.
The single biggest factor we see is surface roughness. And so if you have surface roughness that's significant, and that doesn't have to be much, you'll start to change the reflectivity of the surface. We had a good example of that where we were on paved asphalt, and then there was a section of asphalt which was the same material, but the surface had been essentially ground down and it had a surface roughness of about maybe a centimeter in height and maybe a centimeter across, and that scattering from that roughness reduced the amplitude by about 20%. Even though it's the same material, the reflection or amplitude went down by about 20%. And we've modeled this stuff and you can see exactly that. There's a lot of variability introduced by surface roughness. If you have a thin skim of dirt on the surface or material like that, provided you don't have a very, very high frequency measuring device where that becomes a significant thickness, it probably changes things a little bit if it fills in the surface roughness. But one would expect if it was a thin layer of dust or sand or something like that, you probably wouldn't see much difference. If it's a thin layer of water, then you will see an impact. This test line here, you can see this spike up and down here. That spike here is not really a change in permittivity, but it's a change in surface roughness. In other words, we're seeing a crack or a vertical break in the material that's scattering energy preferentially. So it causes an abnormal change.
We have gone through most of the questions that I can see, and I apologize if I did miss. Thank you, Peter, for doing that presentation. Hoda, I don't know if you had anything you wanted to say.
Thank you, Peter, for your excellent and informative presentation. And thanks to the participants for your time and showing interest in this topic and DPS technology. I personally learned a lot in this webinar, and I hope you did too.